Hello again. So we're still with variable acceleration problems and we're still using differentiation and we're still looking at problems involving maximum and minimum speed or displacement or acceleration. And I've just got three questions which I'm going to start you off with today. These questions are from the same exercise that we started yesterday. So the basic principle is the same as from yesterday's video, but I just want to get you going on these three questions in the hope that you will finish them. So we're on page 188 in the book. Question 4 firstly, and you've got to be really careful that you get this right each time. This is a question about velocity. We're given a v equals equation. It's still relating to t, but this equation tells us about the velocity. Show that p never comes to rest. So that means show that its velocity never goes to zero. So I'm straight away going to sketch that. Here we go. I've typed it in on the calculator, x instead of t. And don't forget you can use your plus and minus button and the cursor just to sort of move around. But this is my velocity axis because it's v equals instead of y equals. And yeah, the graph never comes down to zero. So I've seen it on the graph, and I think plotting a graph is always really good, but this question says show that. And so we need a little bit of extra proof. So I'm going to say, okay, I need to show that there's never anywhere where this equals zero. So I'm going to say, right, this is a quadratic equation. I want to show that this quadratic equation has no solution. There's nowhere where the graph crosses the x-axis. So I'm going to use the discriminant. And we know that we can show that an equation doesn't have a solution if the discriminant is less than zero, if it's negative. So b squared is 9 minus, I always do 4ac in brackets, 4 times 2 times 5. And that's negative, I'm not going to bother working it out. So no solutions. So I've confirmed what the calculator showed me. I'm just going to be absolutely clear. Therefore, I've used that sort of 3 dot thing before for therefore. It means therefore p never comes to rest. Part B, the minimum velocity. So I'm going to just differentiate this. And I am going to, so this is my v equals, I'm going to differentiate it, and then I'm just going to ask, like we did in yesterday's lesson, I'm going to ask when does that equal 0? That will give me a value of t, and then I'll substitute that value of t into the original function, and that will give me the velocity at that minimum point. I know I don't have to worry about whether it's a maximum or a minimum, because I know from my graph it's only a minimum, and I can get gsolve to show me the answer. So I'll know when I've got it right, but I can't actually use the calculator to get the answer. I can only use it to check it. So hopefully I'll be able to finish that one off. So here is question 5. Question 5, we've got a formula for displacement this time. We had velocity in question 4, now it's displacement, the distance that something has moved. And I've sketched it already. There we go. We're told that we're only interested between 0 and 4.5, so that's this section of the graph here. And between that, displacement gets bigger, so this is the particle moving away from its start point, reaches a maximum distance, and then it starts to come back. So 4.5 is when the particle, we're not told anything more about it, has returned to its starting point. So we can copy the sketch, making sure you just mark the key point, so that would be 4.5. Remember, gsolve will give you your roots in this case. So there we go, 4.5, and the y-intersection is 0, so that's nice and easy. But yeah, so this justification here at t is 4.5, the particle has returned to its starting point. So the maximum distance, well again gsolve will tell us the maximum distance. I can get it to work it out for me. It's 13.5 when t is 3, but I've got to show that, so I'm going to do it by differentiating this. Now 9 over 2, when you multiply it by 2, gives you 9, so that's going to be 9t minus 3t squared, and like we've done to find the maximum or the minimum, we just ask when does that equal 0, and then we take that value of t, it's going to give us a value of t, substitute it into the s equation to get the distance. The magnitude of the acceleration at this point, well, sorry, that should be ds by dt, shouldn't it? This is what you get when you differentiate displacement. This is velocity, ds by dt. So if I differentiate it again, that's going to give me 9 minus 6t. This is a formula for the acceleration. So we've got velocity here, which we got by differentiating our displacement function, and then we've got acceleration here, which we got by differentiating our velocity function. Hopefully you'll be able to have a go at finishing that one. And finally, here's question 6. So question 6, we've got another displacement equation, s equals, and this time it's the distance a train moves along a test track. Distance is in meters, time is in seconds, and the test track is 4 kilometers long, and we've got to show that the train never gets to the end of the track. So I'm going to, as always, type it in on my calculator. I am going to sketch it. And first thing I should say, and sorry you can't see it, it is all there. You mustn't be scared when in mechanics you get these horrible equations. Yeah, they are nasty, but we've got these calculators that take away a lot of the fear. So let's draw it. Now, I need to be really careful in this question because of the whole units thing. Distance is in meters, but when I'm told the test track is 4 kilometers, so I need to think, okay, that's 4,000 meters. And time is in seconds, and that goes up to 90. So at the moment, my axes here are wholly inadequate because my time only goes up to 5 and my displacement only goes up to 11 meters. So I'm going to go straight for V window this time, and I'm going to say, okay, let's start from 0 and let's go as far as 90. I mean, they tell me that, so that's nice and easy, isn't it? I'm probably going to change the scale to 10, so I haven't got loads of tick marks. That just puts ticks every 10 seconds. I'm going to leave dot alone. Y minimum, well, I'm going to go from 0 because that's where it starts. And I'm going to go, well, I'm going to go a bit further than 4,000. I'm going to go to 4,200 just so I can see exactly what's going on. And certainly scale, I'm going to change that to 100. And exit and draw. So 4,000 is up here somewhere. This graph never reaches 4,000. The displacement, the train moves along the track, gets further and further away, and then it returns back to where it started. And at 90 seconds, it's back to where it started. Excuse me. So I would always start my answer to this question with a sketch. And I'd probably do something like that to show that it's never reaching 4,000, but that's not good enough. I've got to actually make sure that the location of this maximum is less than 4,000. I mean, gsolve will confirm, yeah, that its maximum displacement is only ever 2,232. But I need to prove that, so I need to find the maximum value of s, which I'm going to do by doing ds by dt. Once I've got that, that will give me a quadratic equation. Once I've differentiated that, I'm just going to ask when does that equal 0. That will give me a value of t, at the maximum value, and I will substitute that maximum value back into the original equation. So those 3 questions are all I'd like you to finish off for this week. What I'm going to do is this. I'm going to put, I know you've got the solution banks to help you, but I'm going to do my own work solution for 4 and 6, just finishing off what I've started in the video. And I'd like you to just to send me a picture of your solution to question 5. And the sketch of the graph and the justification, you can use your calculator for that. Make sure you are marking key points on the axes when you do your sketch. But it's really C and D that I'm hoping to see that you can do successfully. And then we'll move next week on to the final bit of this, which is using integration, which allows us to work backwards. So if we know acceleration, we can integrate to find velocity. And if we know velocity, we can integrate to find distance. Take care.